everyone hears me? Okay, thank you all for coming. It's a great pleasure to welcome you to this workshop on frontiers of optimization for robotics. Now, this is a good first test if everything works. Okay. We have to make the clicker work for the next speaker. All right, so we created this workshop as a response to a lot of cool progress on optimization in robotics. Indeed, you all know optimization is everywhere in robotics, from optimal design to simulation, IK, estimation, calibration, trajectory optimization, motion planning, and recently reinforcement learning. And optimization in robotics also has kind of unique requirements because we have often real-time settings. We have safety critical systems because robots interact with the real world. So we need to make sure that they don't do any damage. But it's also particularly challenging because in robotics we have often a kind of a hybrid nature of continuous and discrete actions or states. We have non-smooth problems and often non-linear and difficult to handle constraints. Of course, there's a longer list of requirements depending on your application area, like high dimensionality as well. And so this means that we need kind of specific optimization methods for robotics. And this has led to a lot of great progress. This is a completely non-exhaustive a list of just really cool works that have been done in the last decades, and going from kind of optimization really specific to robotics to more general optimization tools. And there has been really kind of I would say, a bidirectional flow. Maybe it's a bit more one-directional, like we take a lot of cool tools from optimization and make them work for robotics. But I think the hope is also that maybe we can do things that are relevant for the community and for optimization people in general. So a lot of cool stuff has been done, but obviously we're not done yet. And this is why this workshop also exists. And the goal of today's workshop is really to give a platform for these cool works. We had as an idea, so we actually thought we want to make a workshop from the estimation side. So my name is Frederike, by the way, forgot to say that. I'm working more on the estimation side, and we thought, oh, let's do a workshop on these cool tools that have been developed recently. Then we reached out to more control people, and they said, oh, we wanted to do the same thing, actually. We're already in progress of creating a workshop for RSS. So then we joined forces, and so we had as an idea to make a workshop that's not specific to one application, but really have this cross-pollination to have people from planning, from control, from simulation, learning, and really just talk about optimization in general. We also want to have a platform for nice tools and for open source contributions, because these kind of things sometimes don't get enough credit, and it's a lot of work to make this work and to maintain these kind of tools. And then finally, really just to learn from each other's expertise, because everyone who works in this domain knows there's a lot of tips, a lot of tricks, and it's really kind of a craftsmanship to get certain optimizers to work well. And there's a lot of kind of knowledge that is hard to find and that you can learn from peers. So the idea is also to really have an exchange between experts and non-experts and to learn from each other. And of course, have fun and have good, inspiring discussions and so on. All right. We have a very nice lineup of speakers who we put into 4 categories of like what we considered are important frontiers. Of course, this is not a one-to-one mapping. Many of the speakers have interesting contributions in many domains and along many frontiers. So this is a bit arbitrary, but just to give a bit of structure. So we will have this morning, let me just go to the schedule. So this morning we will have 2 talks about global optimality and geometry, then lightning talks, the coffee break and poster session. So the posters will be here in the room. I believe the coffee will be somewhere outside. I trust you, you can find the coffee. Someone will find it and tell everyone. Then we will have the first session on speed and scale before lunch. Then, then a short break because this is a long session, and then 2 more on optimization through contact. Then we go over to lunch, and during lunch we decided to keep the posters up so that you can keep discussing if you want. In the middle of the lunch break, so at around 1:15, if the afternoon speakers, poster presenters are here, they can already put their posters up then, so we can switch. And that way everybody gets kind of equal exposure, and you can already discuss with the new poster presenters. Then, so in the afternoon, we have the second 2 speakers from optimization through contact, then another session of lightning talks, the afternoon poster session, and then finally differentiable optimization and the closing remarks. All right, we had a lot of nice contributions, so thank you all who contributed to this workshop. We had to, unfortunately, select a few because we didn't have enough space for as many posters as we wished. So this is a quick list of the posters. You can find all of this information on the website too. All right, and finally, just some logistics. So if the lightning talk and invited speakers could always come up to whoever the chair is for that session before the session, that would be great, just to do the setup. The poster presenters can already put their posters up. Some of them are already up. Tim here is the poster chair. So yeah, if you have questions where to put it up or so, please ask him. But otherwise, you can just find a space. As I said, posters for the afternoon can be put up after 1:15. And for the Zoom participants, if you could please stay muted, but you can ask questions on the chat anytime, and we try to monitor the chat. All right, I hope I didn't forget anything, and I just want to take a quick moment to thank all the organizers who have been behind this effort, and thank you for attending. And without further ado, I think we can make sure to set up the first speaker. Yeah, thank you.
So talking about fixing the problem with the pointer, should I do anything with this?
Do you have to break?
Is there a dangle? Oh, there is a dangle.
Oh, okay, that's it. Okay. And then, yeah.
I'll just improvise. Okay, hello everyone. My name is Hen. I will be chairing the first session on geometry and optimality. I think our first speaker will be Professor Luca Carlone from MIT, who was my PhD advisor. So I guess it will be suitable for me to introduce you. So Luca has been, famous for designing certifiable perception algorithms, and I think today he will tell us some more recent advances. Luca, take it away.
Thanks, Henk. Thanks for the nice introduction. It's a pleasure to be here. So as Henk mentioned, I'm Luca Carlone. I'm at MIT. The plan for today is to present a little bit of the recent stuff, but just to give you an overview of this research line on certifiable perception algorithm. So this is kind of like a talk which is talking about applications of optimization to perception and estimation in robotics. So maybe a good way to start is to just stress the fact that optimization shows up in many places when you're doing estimation in robotics, just because standard frameworks for estimation, such as maximum likelihood or maximum a posteriori estimation, ends up like formulating an estimation problem in terms of an optimization problem, right? So if you want to estimate a quantity, we'll end up solving some optimization problem. It's also worth stressing that typically, this optimization problem doesn't work directly on the raw data. We don't optimize directly, typically over images or over high-dimensional data, but it rather happens in the perception backend. So what is the perception backend? To clarify, what is the perception backend, maybe let me start with an example. So the example here is image-based pose estimation. So I give you an image. Typically, in this case, I want to estimate the pose of an object in the image. I'm not going to do an optimization problem right away. I'm going to do first some feature extraction. For example, the feature extraction is going to extract the wheel of the car, the mirrors, the headlights, and so on, different features in the image. And then in the second stage, we're going to solve an optimization problem to find the pose of the car, which is fitting these features as closely as possible. So that's the split I was talking about. There is a front end. The front end is right now typically something based on a neural network. And then there is a back end in which you do model fitting or estimation. And this would be the one based on where you solve an optimization problem. So the example I was giving here was about estimating the pose of an object from the image. You can think that there is pretty much the same split for a bunch of other perception problems. So you have a split in terms of front end and back end for pose estimation of objects in images. You have the same if you're doing pose estimation of objects from point clouds. And even if you do completely different problems, such as simultaneous localization and mapping, you still typically have some sort of split in which there is a front end, which is doing feature extraction, and a back end, which is doing some sort of solving some sort of optimization problem. So the observation here is that a feature of these problems in estimation is that if you compute an optimal solution to the optimization problem showing up in estimation, you typically get a good estimate of the quantity you care about. For example, in this slide, sorry, this is getting the last line where I have the bottom line in many slides, so that is not going to be great. But anyways, so in this slide, I'm showing some trajectory estimation problem. And the point I want to make is that typically in this problem, if you compute an optimal solution, which is the one at the bottom, you get a nice estimate of the trajectory of the robot. If you get stuck in local minima, if you get stuck in suboptimal solutions, instead you get completely wrong trajectories as the one in the middle with gradient descent, or as the one at the top, for Gauss-Newton. So in a nutshell, we really care about getting optimal solution out of this optimization problem. And the bottom line was saying something like, that's why over the last 10 years, we've been focusing our effort on the design of what we call certifiable algorithms. Certifiable algorithms compute an estimate, compute a solution to an optimization problem, and either certify that the solution is optimal or will declare failure otherwise. Okay? So we want algorithms that are able to assess if they got an optimal solution or not. The plan for today is to give you a little bit of an overview of the work on certifiable algorithms for perception over the last 10 years, to be honest. I will start talking about outlier-free estimation problems. That's the initial problems that were solved back 10 years ago. I will talk about more recent work on outlier robust estimation that is more recent. And then I will tell you a couple of things about certifiable filtering and things that we're working on right now. We're very excited about the topics. We have few results, but still ongoing at this point. So we'll start talking about certifiable estimation for outlier-free perception problems. And you will see in the slides, I will mention work from many people. I will give credits to many people, but the phase I want to put in this slide is just to give credit to Dave. I saw Dave somewhere before. All right. Dave is someone that has been doing a lot of initial work with me in this area. Has been really pioneering lots of the development in this area, and I want to feature him in the slide. So back when we started thinking about certifiable algorithms for estimation 10 years ago, we were thinking about a specific estimation problem, which is called post-graph optimization. How many of you are familiar with post-graph optimization here? maybe half, like, post-graph optimization is a common formulation, is a common problem that you solve within SLAM, within simultaneous localization and mapping. And I will not go into the mathematical details, but the objective of the problem is to figure out the trajectory of the robot. So you want to figure out a bunch of poses at discrete time steps along the trajectory of the robot. And you're given a bunch of measurements which correspond either to the odometry, like, the edges between two consecutive poses, or loop closures, which are edges connecting different, like, distant poses. For the sake of the discussion today, you just have to know that post-graph optimization, as the name is suggesting, is kind of an optimization problem. In this optimization problem, you want to figure out a set of positions and rotations. These are essentially defining the trajectory of the robot over time. You're given a bunch of measurements, and you're given like, measurements which are the quantities with the bar. These are essentially position measurements and rotation measurements. You don't need to understand much about the problem per se. Like, you can just think about these as a non-linear optimization problem. So back when we started this research, like, everybody was solving these problems using, you can think about gradient descent, Gauss-Newton, local solvers, essentially, to solve this problem. And back 2014, 2015, we started pushing a little bit of a different way to view these problems. We had back then, like, two main insights, which are pretty easy. Like, in hindsight, like, these are pretty easy, like, insights. The first one is that if you stare hard enough at this optimization problem, you realize that the post-graph optimization problem can be written down as a quadratically constrained quadratic problem, or QCQP. Probably not super surprising for those of you, like, very familiar with optimization. You see that the cost function is kind of quadratic. And if you are an expert, you will think about, constraints in this optimization problem, such as rotation belonging to SO3 as quadratic constraints. More generally, like, if you massage enough, like, this optimization problem, you can write it as the QCQP that I have at the bottom of the slide. And the QCQP is just involving rotation. It turns out that, the translation part of this is very easy to eliminate algebraically. You end up with a problem just in the rotation part. And the problem is involving the rotation. Here, the matrix R is just stacking all the rotation of all the different nodes along the trajectory. And the constraint is just saying that rotation matrices, and that would be amazing if you can get rid of that part. The constraint here is saying something R transpose R is equal to the identity. We're just saying that whatever rotation that we estimate has to be an orthogonal matrix. Okay, so that's the first insight. The second insight is that after you have a QCQP can be easily relaxed to a convex semi-definite program using something that is a standard tool. Is that better? I think it's the same as before. Yeah, it's the same as before. Try fit to window.
But here I can now check. No. Yeah, maybe if I now do fit. Oh.
Yes,
yes.
Right. And if you can remove the side. Yeah, it's probably okay. Yeah. Okay, I think that's great. Yeah. So now a bunch of things will make way more sense. Thanks. Okay, so the insight number one is that we can take this problem in estimation, in particular post-graph optimization, and reformulate that as a QCQP. The second insight is that for QCQPs, there is a standard way to get a convex semi-definite relaxation, which is something that is called the Shor relaxation. The basic idea, if you haven't seen this, is pretty easy. So you have a problem which is a QCQP in the matrix R. So you can think about the R as stacking all the rotation matrices. So it's kind of a tall matrix. And if you see the problem just contains R transpose R, so it will always contain something like, a tall matrix multiplied its transpose. So the basic idea of the relaxation is to say, instead of optimizing R, since R only shows up as R transpose R, we just define an extra matrix Z, which is equal to R transpose R, and we optimize over the full matrix instead. So in a nutshell, what we say is that we are replacing everything which is R transpose R for a new matrix Z. Okay? The advantage of that is that after you do that, you get a linear objective instead of a quadratic one, and you can still enforce the constraints as linear constraints on the entries of Z. The catch here is that the Z has to be, is an outer product of a matrix by its transpose. So it has to be positive semi-definite, which is fine. We can enforce that as a convex constraint. The other catch is that whatever matrix is formed as R transpose R will have low rank. In particular, in 2D, the rank of this matrix has to be 2. In 3D, it has to be 3. But the catch is that, a rank constraint is not a convex constraint. That's why, in the relaxation, you drop any rank constraint on the Z, and that's why, it's a convex relaxation instead. So why, what are the observations about, this relaxation? Well, first of all, we can solve the relaxation, and we can easily check if the relaxation is good or bad. More precisely, if you solve the relaxation, we get a matrix Z. If the rank of the matrix is 2 in 2-dimensional problems or 3 in 3-dimensional problems, then we can extract a certifiably optimal solution for the original problem. So in other words, we solve the relaxation if the matrix we get has low rank, has rank 2 or 3, we solve the original problem we started with, which is a very tough one. Nobody was able to solve that to optimality before. The second observation is that with this insight, actually, you can prove that given a solution is very fast and very easy to check if that solution is optimal. And indeed, what you have to do is just to solve a linear system to check if the solution is optimal or not, which is something that you can do at a negligible cost. It's a sparse linear system. And finally, probably the coolest observation that we were amazed to see, back a few years ago, is that the relaxation is tight, meaning that in practice, you get rank 2 or rank 3 solutions virtually for all realistic noise levels. I remember when we were doing this for 2D post-graph optimization, to break the relaxation, you have to get to noise levels, which you never find in practice. So in other words, we have a convex problem, which is solving post-graph optimization. And post-graph optimization, to start with, is kind of a difficult non-convex problem. Okay? So we are getting a much easier way to solve the problem. What was exciting is that after this work, which goes back maybe 2014, 2016, was just a number of follow-ups, just extending the reach of these certifiable perception algorithms to a bunch of different problems. Here, if you start at the top left, you see the amazing contribution from Dave. Dave Rosen essentially showed that you can do this stuff of relaxation for real on large-scale problems. So essentially showed that you can develop fast solvers for these semi-definite relaxations. And he started proving some theoretical guarantees about when the relaxation is exact and when it's not. There were many follow-ups, both in robotics and computer vision. For example, in computer vision, people studied rotation averaging, showing some performance guarantees. Same tools, exactly the same tools. Briales, back 2017, was able to generalize these to registration problems and essential matrix computation. We did some extension to pose shape estimation. The group, teams group, essentially got to solve landmark-based SLAM and some generalization of SLAM formulations. And this keeps going. If you look at the most recent work I have on the slide, this is CVPR this year. So you still see that there is a lot of ongoing work, lots of progress, and these all quite recent as well. So if I have to summarize the work on outlier-free estimation, essentially with this idea of convex semi-definite relaxations, now we have empirically exact relaxations, which are exact for moderate to large noise. So you can throw a lot of noise in this estimation problem, the relaxations will still work great. For these in particular, we have fast solvers for the relaxation, either because the relaxations have very small size or because you can apply tools from optimization, such as the Buehrer-Montero factorization. And you can do fast optimality certification. So I'm putting an asterisk on the last two because these statements are true for virtually all the problems on the slide, except from one, which is the anisotropic covariances, for which instead we fall in a case which is closer to the outlier case I'm going to discuss next. And essentially, for most of these problems, you can consider them solved. You have an optimality certificate, you have optimal solution, you have fast solvers, and you can check optimality real quick. So afterwards, my group essentially, like, after looking at outlier-free problems, started looking into problems with outliers. The reason for that, and by the way, like, this is work, I'm going to present it, but 90% of this work was done by Hank for his PhD. The context here is that, as I mentioned, like, in perception, we have this perception front end and perception back end. The truth is that the perception front end, which is producing the measurements we fit to the optimization, will produce a bunch of outliers, will produce a bunch of incorrect measurements. For example, like, if you take pose estimation from images, ideally the front end should pick the features on the object you want to estimate, but in practice will contain a bunch of outliers, a bunch of incorrect detections. The same for SLAM. Ideally, like, the post-graph optimization problem should be a nice graph with measurements with well-behaved noise. In practice, many of these edges will be outliers just because of the nature of the front end producing these measurements. So what I'm saying here is that every realistic perception problems will have outliers, and that's why, like, we have to figure out how to extend certifiable algorithms to problems with outliers. So in the previous part of the presentation, I was arguing that we can phrase a lot of problems essentially as non-linear least squares. We can estimate whatever variable we want, and we are going to estimate the variable by minimizing a non-linear least squares problem in which the residuals will depend on some measurements, and we'll have some residual function here which will measure how well a state, like an estimate X, will fit the measurements. In the next part of the talk, I'm going to make these a little bit more complicated. It turns out that in the presence of outliers, you don't want to do least squares. You want to add a robust loss function. Okay, so you want to add a function which gives you some robustness to outliers. The use of robust loss functions is something that has been well known, like, robust statistics for the last, like, 40 years plus. The basic problem that we try to solve is that while people in statistics told us that you have to put a robust loss function to optimize, to solve estimation problem with outliers, they didn't tell us how to solve this optimization problem. So indeed, it is provable that for typical choices of robust loss function, this optimization problem is NPR. You cannot solve it in polynomial time. So what people in robotics and vision do, I will trivialize the state of the art with just two potential approaches. The first one is local solvers. Think about, gradient descent. Gradient descent is great, but, we'll need some initial guess, and it's very easy for it to be stuck in local minima. The second approach, which is super popular in vision, is RANSAC, in which you try to solve an optimization problem like this through sampling. RANSAC will probably fail if you have too many outliers, will probably fail. Moreover, like, RANSAC will mostly apply to low-dimensional problems, so will definitely not apply to things like, post-graph optimization. And something like, that really concerned us when we started this line of work is that the existing algorithms will essentially give us an estimate for the X, for the variable we care about. This estimate can be completely off, but the algorithms will not be able to tell us whether the estimate is good or not. So that's why we started thinking about, can we develop certifiable algorithms to problem with outliers? And again, here we have two basic insights. We want to solve a problem like this, in which we have a robust loss function, and we want to estimate the X. The first insight is pretty similar to the one I had in the first part, but is a generalization of that. The first insight is that a large set of robust estimation problems in perception can be formulated as polynomial optimization problems. So polynomial optimization problems are nothing scary, are just an optimization problem in which both the objective and the constraints are polynomial functions. Okay, so no longer quadratic functions, polynomial function. It's just a generalization of what I said in the first part of the presentation. How do you show that? By inspection. You take a bunch of problems in perception, registration, SLAM, structure from motion, all these different problems, and you show that you can massage the math into something that is a polynomial optimization problem. For example, if you take registration problems in which you align 2-point clouds, it's pretty easy to see that the objective is a quadratic function, and the constraint as well will be some quadratic function in this case. A bit more complicated, but you can also show that after you add a robust loss function, the objective and the constraints will remain polynomials. And we show that for a large variety of robust loss functions as the ones on the slide. I will not go through the math, but at the end of the day, with these robust loss functions, you can just rewrite the math. And rewrite them as polynomial functions. The only thing that changes is that instead of having quadratic polynomials, now you will get to cubic polynomials, but it's pretty much the same as before. So great. With this first insight, we have essentially rephrased most of estimation, robust estimation for robotics as polynomial optimization problems. But the truth is that we haven't gained much in the sense that polynomial optimization problems is a very nice and general class of problems, but it's still hard to solve. That is where the second insight comes. The second insight is that polynomial optimization problems can be relaxed in a very standard way to a convex semi-definite program using a tool which is called the Lasserre hierarchy of moment relaxations. So you see the parallel with respect to the first part. In the first part, we had QCQP, and we did short relaxation. Now we have a more general class of problem, which are polynomial optimization problem, and we can use this tool, which is called Lasserre hierarchy of moment relaxations. And I will show you in a bit, how this works. So let me give you an example, actually, of how it works. We want to solve a polynomial optimization problem. Again, this is non-convex and it's probably hard. I will tell you, just in one slide, how the Lasserre relaxation works. And for the sake of this explanation, I'm going to assume that the degree of the polynomials is less than 4. That's actually what you have in perception. Most of the things are dimension, are degree 3 polynomials. And I'm going to assume that the variable is just two-dimensional variable, x1 and x2. That is not true. In typical problems we solve, the variable is high-dimensional. But just for the example, let's assume we just have x1 and x2. So in order to build a Lasserre relaxation, you have to do two things. First of all, you have to define a monomial basis. A monomial basis is just a vector containing the variable you want to estimate, but a little bit more. Will contain monomials, which are function of the variable you want to estimate, of degree, in this case, up to 2. Okay, so instead of just containing x1 and x2, we'll just contain x1 square, x1, x2, x2 square. In other words, we're essentially over-parameterizing the state we want to estimate. Not only we estimate x1 and x2, but we also estimate the power of x1 and x2. The second step is to define what is called the moment matrix. The moment matrix is just the monomial vector multiplied its transpose. You can think about this just as a large matrix, which contains all the monomials of the variable you want to estimate from degree 0 to degree 4 in this case. Okay? So in other words, we are putting together all the variables in our optimization problem and the corresponding high degree, the corresponding power in a large matrix. Why is that a good idea? Well, the insight is actually pretty simple. The insight, which is definitely not in this slide, is this one. The insight is that if you're computing, if you have the moment matrix, which has all the variables from degree 0 to degree 4, you can write any polynomial of degree up to 4 as a linear combination, as a linear function of this matrix. Okay, so whenever you have degrees, whenever you have polynomials of degree less than 4, you can write them as linear function of this matrix. So in other words, we can rewrite these polynomials here as just linear function of the moment matrix X. Okay, so linear objective, linear constraint. So great, we transform a hard problem, and through defining this moment matrix, we transform that into a linear problem in which you have a linear objective and potentially just linear constraints. What is the catch? There must be a catch. We started with a hard problem. We cannot get a linear problem out of it. The catch is that the moment matrix is not any matrix. It's a very well-structured matrix. And in particular, the matrix, again, is PSD, is positive semi-definite, which is fine. We can enforce that. But is also a rank 1 matrix, which, same story as before, is a non-convex constraint. We have to relax that. We cannot enforce that in a convex optimization framework. So the relaxation is about relaxing the rank of the matrix and getting just an SDP, which is something convex, which is relatively easy to solve, as a relaxation of the original hard problem. The truth is that for Lasserre relaxation, you have to do a little bit more. Not only you have to drop the rank constraint, but you also have to add a bunch of external additional constraints. For example, the constraints are enforcing that many entries on this matrix will be repeated. For example, this entry will show up at a bunch of places in the matrix. So you have to constrain the entries to be the same. But essentially, you just have to add multiple constraints to make the relaxation work. So I'm running super late here. So we'll probably like, just tell you why. I will not go through the theorem for sure, but I will tell you why this laser relaxation is something that really caught our attention. The laser relaxation in a nutshell is transforming a hard problem into a convex semi-definite problem. And the properties of the relaxation are what are very cool and what motivate us in our investigation. To summarize the theorem is saying two main things. The first thing is saying if you solve the convex relaxation and you get a rank 1 matrix, then from the rank 1 matrix, you can compute a provably optimal solution to the original problem. So if you can compute a rank 1 matrix, you are done. You have a provably optimal solution. And the second property is telling you that if you increase the size of the relaxation enough, you always get a rank 1 matrix under mild conditions. Okay, so essentially, this is a recipe for solving any sort of polynomial optimization problem. What is making these relaxations even cooler in our setup is that empirically we see that we get rank 1 solutions in most of the problems, perception problems that we solve. So the relaxation is commonly tight or is producing rank 1 solutions. Not only that, but it's tight when the relaxation is not too huge in size, so for small relaxation order. It remains tight in common perception problems. And this, in turn, allows concluding that for the first time, you can solve robust estimation problems showing up in robot perception to provable optimality or compute a suboptimality gap in polynomial time. So these we've been applying to many, many problems. This idea of outlier robust estimation, you can apply to, how much time I have? 2 minutes? Yeah. Yeah. So you can apply these to many problems, rotation averaging, registration, pose estimation from images, rotation averaging, and so on. And the story that you get is always pretty much the same. The rotation, the relaxation is tight. Even if you have a large amount of outliers, the relaxation will eventually break only if you have a huge number of outliers or a huge amount of noise. And there is a bit of a difference, which is the last thing I want to point out. The relaxation is exact for moderate noise and outliers. But for this setup, there is no fast solver or no fast certification because you end up getting fairly large scale semi-definite programs, and you cannot apply tools like Buehrer-Montero, for example. So with that, I think what I have time to cover is my conclusion slide. Clearly, I didn't get time to get to the last 3 slides, which are certifiable filtering. But what I want to stress is that we try to release a bunch of open source resources and tools for these certifiable algorithms, both without outliers and with outliers. So you can check those out. And I will stop here and thank you for your attention and thank the sponsors supporting the work.
Can we present from your left hand? Because the next speaker is from me. How does it work? So normally we just share.
You can take a
question. Maybe we have time for one question if there's one.
Great work, Luca. Thanks a lot. So we can certify the solver, but what about feature extraction? So that's the underlying assumption. And the follow-up question is, you said typically all these optimization problems rely on features, but there are also optimization problems that go back to the raw data, like photometric bundle adjustment. So can we unify everything?
Yeah, but great questions. For the front end, let's say that certified front end, that is not an optimization problem. So you could have So the front end is not an optimization problem. So you have to redefine what it means certification. The good news is that there are tools in that sense, that you can use to guarantee performance, for example, conformal prediction or other tools, but there will be more tools about guaranteeing the output of a neural network. And by the way, Hank has done cool work on on that front as well. So you have tools to do that, completely different from optimization. Regarding the second question, true, you can have photometric errors and so on. In particular, in the outlier case, the size of the problem that you have to solve grows with the number of measurements. So you don't want to do you don't want to do very large scale. That's why we stay away from photometric error. And also you have to be careful about the expression of the objective that you minimize, because of course it has to be a polynomial. Yeah? We are not claiming that we can solve all the problems. You have to see if the objective of your problem is a polynomial. I'm not sure it is for the photometric error. I bet it's not.
Any other questions?
It's something like, if for all the problems I was listing, registration, postgraph optimization, and so on, the degree of the objective is typically 3. In the outlier-free case, it's actually 2. You just have quadratic objective. It becomes 3 with outliers because with outliers, the trick is that you can rewrite a robust loss function by adding extra variables. These extra variables will multiply the objective, so will make degree 3. In the Lasserre framework, you need an even degree, so you cannot do 3. That's why like 4. Yeah, but it's without loss of generality. Like that is fine. Yep. Yep. Yeah, so definitely, like, in the case of outlier free, like, the size of the noise is what influences the tightness. In the case of outliers, both the noise and the number of outliers will influence the tightness. There are very few results, like, there is a single result program I'm aware of saying for this amount of noise, the size of the relaxation will be tight. And this is a beautiful result. For postgraph optimization will tell you that essentially the relaxation is tight if the graph is well connected and the noise is not crazy, but it's very tough to get this kind of results in general. So I do not have a general recipe. Like, we just have empirical observation of noise versus tightness. Great question. Yeah.
Okay, let's give Luca a round of applause. And then, okay, so our next speaker will be Noémie Jaquier so she is a postdoc researcher at the High Performance Humanoid Technology Lab at KIT. And today she's going to tell us geometry-aware Bayesian optimization for efficient robot learning. And let's test the mic, maybe.
Okay, hi, can you hear me?
Yeah, I think we can hear you. Let me just...
Okay, perfect. Ben, can I go ahead or?
I think you can get started, but I was trying to disable the sound here, but it seems to be...
Okay, then I'll get started. So thank you very much, first of all, for the kind invitation. It's a really cool workshop, and it's a pity I cannot be there with you today in Delft. But okay, I mean, it's like that for this time. So today I would like to talk to you a little bit about how to actually do more efficient Bayesian optimization by leveraging the geometry of the data. So the main idea is that robotic manipulation involves complex skills, and some of those skills can involve, for instance, the pose of the robot to be precise, or the robot to be stiff or compliant in specific direction. And in general, we would like our robot to be able to cope with uncertainties in the task and to generalize skills to unseen situation. So for instance, if we tilt the hole, we would like the robot to be able to adapt its orientation so that the insertion task is still fulfilled. And in other tasks, control policies actually have to be adapted during the policy, during the execution of the task. For instance, you may want to have a different final stiffness, so a different stiffness when you are approaching the hole or when you are inserting. So controller policy parameters often have to be refined and adapted in robotics. And because we are working with real agents, we would like to actually have safe, fast, and data-efficient learning and adaptation process. And one algorithm that is well suited for that is Bayesian optimization. It has actually been growing in robotics, so the interest has been growing in robotics because Bayesian optimization is able to efficiently solve challenging optimization problems. And one way to make Bayesian optimization even more efficient is to add some inductive bias, so some basically prior knowledge about your problem directly inside the algorithm. And this has been shown to actually improve the performance of Bayesian optimization in several types of problems. What we can do also is to actually take into account the geometry of the search space. So in the example I showed you, for instance, when we want to adapt the orientation of the end effector, we usually represent orientation as unit quaternion, which are vectors with a unit norm. Or when we want to adapt the stiffness, basically the stiffness are similar to positive definite matrices, so they have only positive definite eigenvalues, and all those parameters have specific geometry. So what we can do is to take the geometry of the search space as inductive bias and to improve the performance of Bayesian optimization. So to give you a few examples of robotic parameters that feature such type of geometries. So first of all, we have the classical Euclidean space, which I think all of us know and work with all the time. So we use this to represent position, forces, and torques, among others. We have the sphere manifold. This is my example of the previous slide, which we use to represent orientations and directional data. The other example of the previous slide, which are symmetric positive definite matrices that we use for control gains, stiffness ellipsoids, inertia matrices, manipulative ellipsoids, and others. We have the torus, which we often use for joint configuration and is usual to represent periodic functions. We have the special orthogonal group for orientation as the building blocks for other types of geometries. And finally, a last example is the hyperbolic space, which has recently been, the interest for it has recently been growing for graph and tree embeddings. So what we would like to do is to take into account the geometry of all the spaces to improve Bayesian optimization. So all the spaces actually are Riemann manifolds, so we can take the geometry from that types of mathematical space, and I will go a little bit later into details on how we actually do that. First of all, I would just like to recap a little bit what Bayesian optimization is, so that all of us are basically on the same page to see how we then introduce geometry to improve it. So Bayesian optimization is basically a global is a black box. It is aiming, at optimizing black box function to find global optimizers. So we have an unknown function f. We don't know the exact form for this function. We don't have a formula for it, but we can observe it at any point in the search space. And then Bayesian optimization, what it does to find the global optimum is iterating two steps. The first step is to model the subjective function. It's typically done with the Gaussian process. So we put a Gaussian prior on the function, and then by computing the posterior of this function based on our observation, we obtain a mean, which gives us an estimate on how the function looked like, as well as a measure of uncertainty, so the covariance of the posterior, which tells us how close or how far we are from our observation. So this is here the gray, blue-gray envelope that you see on the model. Once we model the subjective function, what we do is that we want to know where to query the next point. So for that, we evaluate the utility of candidate points with the so-called acquisition function. The acquisition function is built based on the posterior of the Gaussian process, and it aims at trading off between exploration and exploitation. So exploration, because we want to explore where actually we have high uncertainty in our model, and exploitation, we want to exploit where we know that the mean could actually be small, and then to find this optimum. So we define this acquisition function, we maximize it, and the next query point is given at the maximum of this acquisition function. And then we iterate those two steps, and typically Bayesian optimization converges fast to a global optimum. So when we want to now have a search space which has some specific geometry, so a search space which is not Euclidean but a Riemann manifold, we have to take into account 2 points. The first one is that the Gaussian process, so the model of the function, is completely specified by the mean and the covariance function. So the mean is typically a constant, we will keep it like that. But the kernel function in the usual Euclidean case is usually defined as a function of the Euclidean distance between points. Now, if you imagine that you have a space which is non-Euclidean, so here you can think about the sphere, measuring the Euclidean distance on that space actually doesn't make any sense. So if you want to measure the distance on Earth, you don't measure the distance through Earth, you actually measure it on the surface. So what we do here is that we reformulate those kernel functions so that they take into account the geometry of the domain with a Riemannian formulation. I will go into details of that after. The second point that we have to take into account is that the quality of the next query point depends on the optimization of our acquisition function, so of the quality of this optimization. Again, usually when we have a Euclidean domain, we simply optimize over a subset of the Euclidean space. And what we usually do when we have constraints, we add actually some constraint, and we have a constraint optimization process. What we can do here to improve this optimization is to actually directly optimize on the space of interest. So in that case, it will be on the Riemannian manifold, with an unconstrained optimization setup. So I've been talking already, I told you I'm aiming at optimizing over Riemannian manifolds, but I didn't really formally introduce what those manifolds are. So let me give you now a brief overview on Riemann geometry that will basically present you the tools that we need to then reformulate the kernel function and the optimization when we have search spaces that are Riemannian manifolds. So very intuitively, a Riemann manifold is a mathematical space that locally looks Euclidean, but is curved. When I say locally looks Euclidean, is that you can take any neighborhood on the manifold, and you can find a homomorphic mapping from this neighborhood to a subset of the Euclidean space. Then this allows us to define the notion of tangent space on manifolds, which are the space that are literally tangent to the manifold at a point. And when the manifold is Riemannian, what we do is that we can define an inner product on these tangent spaces, which is called a Riemannian metric. So it's symbolized by a Riemannian, by a symmetric positive definite matrix, which smoothly varies across tangent spaces on the manifold. This Riemannian metric is super important because it captures the full intrinsic geometry of the manifold. So basically, if you know your Riemannian metric, you can do everything. So for instance, you can define the norm of vectors on a tangent space. You can define the length of curves on your manifold. You can define the distance between points on the manifold. And you can define the generalization of straight lines on the manifold, which are called geodesics. Based on this Riemannian metric, we can also define mappings from the manifold to the tangent space and vice versa. This will be useful actually when I will show you the generalization of the optimization to Riemannian manifolds, of the optimization of the acquisition function. So what we do here typically is that we use the logarithmic map to map a point from the manifold to the tangent space. This tangent space is Euclidean, so then you can operate as usual with your vector. And once you did so, you can project the result back onto the manifold using the exponential map. And a last operation that we'll use, and that is very often useful, is the parallel transport operation, which allows us to move vectors across tangent space in a geometrically consistent way. Okay, so now we have the tool. Let's go back to what we actually need to change in our Bayesian optimization algorithm to operate with Riemannian search spaces. So first of all, for the kernel. So here, I will show you basically how we can generalize the squared exponential kernel, so the one that are very often used with the Euclidean distance inside, to the case of Riemannian manifolds. So to do so, we actually have to take an alternative view of Euclidean squared exponential kernels. So squared exponential kernels in Euclidean space can actually be seen as the covariance of a random process. And the random process has to satisfy the stochastic partial differential equation that you see here on the right. So the W that you see here is the white noise, and this triangle is the Laplacian operator. And basically what we do is that you solve this equation, you find the result for F. And once you have the formula for F, you compute the covariance of it, and this is your kernel. So in the case of compact Riemannian manifolds, so when I say compact, is manifolds such as the sphere, the torus, and SO3, for example. So in this case, what we can do is to actually take this view of kernels and generalize this stochastic partial differential equation to the Riemannian case. And then again, we solve the stochastic partial differential equation, we compute its covariance, and we obtain our Riemannian kernel. So the generalization requires that we actually replace the Euclidean white noise by the white noise with respect to the Riemannian metric. So remember, this Riemannian metric is this inner product defined on the tangent space. So we basically, here it allows us to introduce the geometry into the noise. And then we use the generalization of the Laplacian operator, which is the Laplace-Beltrami operator. And again, it's defined fully based on the metric. So you see that this Riemannian metric really comes everywhere. So the G that you see here in the equation is the metric. So we solve this equation, we compute the covariance, and this is the type of kernel that we obtain, where the lambda and the f's are the Laplace-Beltrami eigenvalues and eigenfunctions. So you see basically our kernel is an infinite sum of those eigenvalues and eigenfunction of the Laplace-Beltrami operator. And for those of you who are familiar with the Mesh-Red theorem, you can see that it's actually very similar. In Euclidean space, we actually have also kernels that are defined as infinite sum of eigenvalues and eigenfunctions. So to give you an example on how those kernels look like, you can see here the formula for the kernel on the circle. And you see that basically we have, again, here this infinite sum over the space of integers this time. And we have this here, x and y are the 2 points that we are given as input to the kernel, and we have this integer n. And what you see is that this part that is here in blue is basically all the possible distances between the 2 points on the manifold. So when n is equal to 0, you have the shortest path. When n is equal to -1, you take the distance between the 2 points in the reverse path. When it's +1, you do a full tour on the circle plus a little bit, etc., etc. So basically, you take into account all the possible paths on the manifold. So this was for the case where the manifold is compact. We don't have only compact manifold in robotics. So if you think about typically the manifold of symmetric positive definite matrices or the hyperbolic space, they are non-compact, and this generalization doesn't work in that case. So what we can do instead is to leverage the relationship between the heat kernel and the squared exponential kernel. So the heat kernel is actually available in the literature for various manifolds, and we can basically leverage the fact that the squared exponential kernel is a rescaled, reparametrized version of this heat kernel. Now, in general, it's true that the squared exponential kernel is very often used, but if we want something that is not necessarily as smooth as the squared exponential kernel, we may want to use a matter kernel. And in that case, what we can simply do is actually to define the matter kernel as an integral of the squared exponential kernel over basically the length scale parameter, as you can see here. So this gives us our kernel. It allows us to generalize basically the Gaussian process, so the model of our function that we use for Bayesian optimization. Now, the second part that we have to adapt is the optimization of the acquisition function. And to do so, we use optimization methods on Riemann manifolds. So I will show you here the example of the conjugate gradient descent on Riemann manifolds, but that works with many other algorithms. So the idea is that we want to maximize our acquisition function, so equivalently to minimize minus our acquisition function. And we always start with an iterate on the manifold and with a search direction which lies on the tangent space of our iterate. The first step that we do is that we want to find where is the next iterate for our optimization. And for that, we start by solving a line search problem, which will give us basically how far we have to go along the search direction. Once we find the scalar function that tells us how far we go, we can then use the exponential map to map the rescaled search direction from the tangent space onto the manifold. After that, we want to be able to find the next search direction. So to do so, we first parallel transport the previous search direction on the tangent space of the new iterate. And then we compute the gradient of the function, and the gradient is again a function that lies on the tangent space at the current iterate. So you see the importance here of using those tangent spaces. Then we can combine the new search direction, the parallel transported all search direction and the gradient, and this gives us the new search direction. And we iterate those two steps until convergence. And then the point that we're going to query with our Bayesian optimization algorithm is basically the point here that we find with this conjugate gradient descent. So let me show you how this works on different benchmark functions. So here we have the Ackley function on the sphere, as well as 2D projection. So you see that here the two axes at the bottom are the two axes that we have here. And here x2, x3 is those two axes there. And this axis here is the value of the function. And what we aim at doing is to find the global optima of this function, which is here circled in red. So I will show you the evolution of the Gaussian process mean on the sphere, as well as the evolution of the Gaussian process mean and variance. So the variance is here, this gray envelope on the 2D projections. So, and I will show you also the evolution of the current best that we have for this function. So the global optima is actually 0. So you see here, we start the Bayesian optimization, so we're querying the points, and at the beginning we have an exploitation phase where basically very quickly we reach something that is close to the global minima, and then we have an exploration phase where basically the model Bayesian optimization reduces the model uncertainty. So you see that the gray envelope is becoming smaller and smaller, and after 45 iteration or so, we have actually a good model of the entire landscape of our function. We can have a look then at the convergence statistics of the models. So here we compare our Riemannian Bayesian optimization approach with Euclidean Bayesian optimization, where we use the Euclidean squared exponential kernel and where we simply use a constrained Euclidean optimization algorithm. And those two in blue and orange are the two Riemannian kernels, one with a matter was one with a SK kernel, and the two on the top here are the Euclidean ones. So you can see that with our approach, we converge faster to better accuracy and to a lower solution variance compared to simply using Euclidean approaches. Now to show you this on a couple of actually robotics problems. So here we consider task-compatible manipulative optimization scenario. So it's a common problem in robotics where usually solutions actually do not exploit the geometry of manipulative ellipsoids which lie on the manifold of symmetric positive definite matrices. So what we would like to do here is to have this planar robot tracking a desired Cartesian velocity trajectory that leads to a vertical line while tracking a manipulative ellipsoid in the null space. We have a velocity controller, so we follow here this vertical line at a given speed, and then we have this manipulative tracking in the null space. And what we aim at optimizing for is the desired manipulability, which is here m hat in green. And we want to optimize this desired manipulability such that the end effector jerk of the robot is minimized, such that the manipulability is then aligned with the motion direction to facilitate moving along this direction. And we want actually to have manipulability that we are able to track. So we don't want to optimize for manipulability that the robot cannot track anyway. So you will see here the iteration of Bayesian optimization. So this is the first few ones. The manipulability, desired manipulability is in green. This is the one that we're optimizing for. And the one that is tracked by the controller, that is reproduced by the controller is the purple one, which is the current manipulability. And you see that at the beginning of the iteration, the manipulability is not really aligned with the motion direction and the robot is not really able to track it properly. And you will see that after a few iterations, basically, the manipulability gets aligned with the motion direction and the robot is able to track it better. And you see on the right that the cost function is actually dropping and reducing everything with more iterations. And I will show you now the best after 100 iterations. So you see that the manipulability is aligned with the motion direction and the robot is actually able to track it most of the time. We can have a look at the convergence statistics. Again, the remaining one is here in orange, and you see that it actually converges faster, better, and with lower solution variance than the Euclidean ones, which are typically here the three that you actually see here on top. And we also put this approach on a real robot experiment. So here we have our RMR6 robot in the kitchen that aims at opening the dishwasher, and we are aiming at optimizing for the orientation of the end effector. So we have a very simple policy. The robot approaches the dishwasher. When it makes contact, it slides the hands up until we actually grasp the door handle. So our cost function here, we want to have at the end a short distance with the door handle. We want to have low external force, so low contact force with the dishwasher to avoid breaking basically the robot hand. And we want to have a high volume force manipulability to be able to open the dishwasher at the end. So you will see here the initialization of the Bayesian optimization. So this is with a random orientation at the beginning, and we have too high contact force, so the robot cannot go until the handle. So what we're optimizing is here the orientation of this end effector, right? And then we do few iteration, it gets better and better. And then I will show you at the end the best that we obtain after only 15 iterations, and you will see that we are actually able to open the dishwasher. Okay, so this is our optima after 15 iterations. You see that we have a low contact force, we can reach the door handle, and we have a manipulator that is high enough to give the force to the robot to finally open the dishwasher. Okay. So basically, until now, I showed you that the performance of Bayesian optimization can be improved by introducing domain knowledge in the form of geometry awareness. And I showed you that we actually have this geometry-aware Bayesian optimization algorithm, which allows us to efficiently optimize robotics parameters that lie on Riemann manifolds. So in the last few minutes, one of the core problem of Bayesian optimization is actually that it doesn't scale well with high dimensions. So I would like to spend the last few minutes showing you how we can actually improve that, again, from a geometry-aware perspective. So we have many parameters that belong to high-dimensional Riemann manifolds. This is the case in machine learning, but also the case in robotics, typically for controller parameters or inertia matrices, which can be very high-dimensional symmetry positive definite matrices. And in several examples, as you can see here, basically we don't need all the dimension of those parameters for the Bayesian for be able to fulfill the task. So in the case here where we want to push blocks on a table, we can have those two stiffness matrices and the result will be exactly the same. So basically the vertical dimension of the stiffness matrix doesn't matter here. So it means that the cost function actually evolves along a low dimensional latent space. And in that case, actually, we can optimize not on a 3x3, on the 3x3 space of SPD matrices, but only on the 2x2 space of SPD matrices that is on the plane. So the latent space on which we actually want to optimize our variable preserves, in that case, the manifold structure. You can see here another example where instead of optimizing on the sphere, we can simply optimize on a circle. And actually, this is also the very key assumption that is often used in Euclidean high-dimensional Bayesian optimization algorithm. So what we did here is that we proposed a high-dimensional Bayesian optimization algorithm on Riemann manifold. So we assume that the objective function satisfies the low-dimensional assumption and that it varies only along a low-dimensional latent space, which inherits the geometry of the original manifold. So in the example here, we are optimizing on the manifold S2. It's not really high-dimensional, it's just for the illustration. And basically, we will be able to have a mapping onto a lower-dimensional manifold of the same geometry, which is the circle S1. So what we do is that we learn a structure-preserving parametric mapping, which goes here from the sphere to the circle. And then we build our model, so the quotient process, on the low-dimensional manifold, so here on the circle S1. So basically, we optimize jointly the parameters of our structure-preserving parameter mapping and the parameter of the kernel function on this low-dimensional manifold. Once we have this, so this is optimized, by a maximum likelihood estimation jointly. Once we have this, we define the acquisition function on the latent space, so on the low-dimensional manifold, and we optimize for the next candidate point in this low-dimensional latent space. And then once we have the candidate point, we map it back onto the high-dimensional manifold with the pseudo-inverse of our structure-preserving parametric mapping. And we iterate basically those two steps. So I will show you a couple of results on benchmark functions. So here,
Noémie, I think maybe we have to speed up a little bit and maybe you can finish in the comment also.
Sorry? Yes, I can hear you.
I'm saying that maybe you can finish in 1 minute for the sake of time.
Yes, this is my last slide. Yeah, okay, sorry for that. So yes, so here you can see the result of our high-dimensional algorithm is actually here this brown curve. So again, we often converge faster, and it actually consistently converges fast and provide good optimizer when compared to Euclidean high-dimensional BO approaches. Okay, so to conclude, what I wanted to show you here is that relevant robotics parameters feature a variety of geometries. If we consider the geometry for Bayesian, but not only for optimization in general, we can reach faster convergence, better accuracy, lower solution variance, and we improve the scaling to high-dimensional problem. And I hope that with that, and it's not only for optimization, I kind of try to convince you that geometry is actually a powerful and expressive form of inductive bias for robot learning. So thank you for your attention. These are the papers associated with what I presented today. And if you're interested in geometric method, we recently gave here a tutorial at ICRA, so you can find the videos in this QR code. Thank you very much.
Okay, maybe just one question, if there is one.
Thanks for the great talk. I just had a question about, so for the acquisition function, you're essentially solving an optimization on a manifold. Based on the previous talk, we know that that can often converge to local minima. So I was just wondering if you noticed that ever in your optimization, or if you used any certifiable methods to deal with it.
So yes, indeed, sometimes we converge to local minima. I think at the end of the day, those techniques to optimize on manifolds, they have kind of the same properties as the same algorithm, but in Euclidean space. So if you use a gradient descent, this is prone to local optima. Then you could, on top of that, add some certifiable methods or that kind of things, basically, to ensure that you don't.
Great, thanks.
Thanks.
Okay, thank you, Noémie. And let's go to the spotlight session.
Thank you.
So I think for the morning spotlight session, we have two papers. The first one is MPCC++. model predictive contouring control for time optimal flight with safety constraints. And then the second one is a functional Newton method with sparse gradient projection for motion planning.
Thank you. So do you hear me? Well, yeah. I'll be talking about model predictive contouring control for time optimal flight. My name is Noémie Krinner, and this is joint work between Professor Scaramuzza's group and Professor Zeilinger's group. So first of all, what is time optimal flight? The goal is to fly a drone as fast as possible. And this is a very challenging task and really requires pushing the limits of the platform. So it also makes it a very interesting benchmark for us to sort of push artificial intelligence in robotics. And in fact, in 2022, for the first time, an AI went against a world-class human pilot. But these algorithms struggle to prevent gate collisions and often plan too close to the edges of the gates. So the question is, can we do better? Can we fly fast and safe? So there are two ways to solve this problem. One side, we have reinforcement learning. So here we have an end-to-end learning framework, and we directly learn from interactions with the environment. And then there's sort of the optimal control side. So here we actually leverage a physical model of the system, and we can include constraints, but we need to solve an optimization problem online. So we're going to talk about the optimal control side in this work, and in particular, we're going to look into model predictive contouring control, which is an MPC algorithm sort of tailored for racing applications. And it does so by compromising between two conflicting objectives. So at one side, we sort of want to maximize progress along a specified path, while at the same time, we want to keep tracking this path accurately. Now, you may wonder, how do we actually can make the drone fly through the gates? Like, can we come up with something like a track in this 3D space? You may think, for instance, in car racing, we have a very specified track, but can we do something similar for the drone? And in fact, we can. So we can come up with a tunnel which passes through the gates, sort of expands in the gate-free regions and constricts in the gate passages. So the idea behind this is that we really let the controller sort of plan the fastest trajectory within the constraints. So we've addressed this part of flying safe, but what do we need to fly fast? We actually need a very good prediction throughout the MPC horizon. So what we do is we augment the nominal system with a residual term that we infer directly from real-world data. And of course, as with any control problem, we also need good parameters of the controller. So we actually can use Bayesian optimization to tune the controller parameters. And we use a specific scheme that's called trust region Bayesian optimization. It does global Bayesian optimization. So the idea is we put all of these elements together, the residual learning, the Bayesian optimization, the safety constraints, we train in simulation, and then deploy our approach in the real world. And you can see that we can fly very consistently over and over again without crashing into the gates. So this is really the first approach to achieve 100% success rate. And the nice thing here is that we sort of achieve this safety without compromising performance, as this approach achieves similar lap times to the best performing state-based RL controllers. So one thing that I didn't mention so far is we're using a motion capture system to do this. So there's sort of no split state estimation. And with this, I'm at the end. Thanks a lot for listening.
Okay. The next speaker.
Hi everyone, I'm Jiayun Li. I come from the computer science department of TU Darmstadt in Germany. I work with Georgia Havazaki on the topic of functional Newton method with sparse gradient projection for motion planning. So the trajectory transcription in trajectory optimization is very crucial for like determining the definiteness of the corresponding optimization problem. So, and defining trajectory in vector value RKHS has proven to be an promising problem approach to improve the definiteness of the optimization problem in trajectory optimization. And the multivariate trajectory defined in vector value RKHS with finite support has the following form, where the capital K is a kernel matrix function that makes the following inner product in the Hilbert space positive definite. And this inner product will induce an outer product and also the RKHS norm. And this framework is highly representative, therefore can better represent the nonlinear correlation in time and also the joint-wise correlation. But this approach is very expensive for robots with high degree of freedoms, and the choice of matrix kernel function is very challenging. So we mainly focus on the first challenge, and we propose to use functional BFGS and sparse gradient projection to mitigate this issue. With the inner product and outer product in Hilbert space, it's easy to check that the second equation and the Sherman-Morrison formula are both valid, which are the prerequisite for the BFGS technique. Then we can write the functional BFGS update at the following equations, and you can see on the right-hand side the compared with the momentum acceleration algorithm, such as the conjugate gradient descent, the BFGS can provide a significant acceleration in convergence. In trajectory optimization for better constraints compliance, we usually add more time points, or we compute the gradient through interpolation. But this kind of approach will reduce the performance of the optimization algorithm. But in vector value RKHS, the gradient through interpolation has a closed form solution by solving the following least squares problem. And we call it the sparse gradient projection. So we can obtain better trajectory, but with acceptable computer overhead. Yeah, thank you for your attention. If you're interested, please visit our poster for further discussion.
I guess we'll go to the poster session.
Yeah, so just one quick note for the poster session. I think to not have to, because it's a bit crowded, we will have a few posters in here and a few posters out in the area. So if you haven't put up your poster yet, you can come see Tim and Connor, who are moving the green boards right now, and myself, and we can help you put up the poster somewhere. Thank you.